Visual weld inspection, defects, gauges, and process control. Module 9, weld inspection mastery, the complete NDT NDE course. Gary Pace, PE, welding engineer. So visual inspection, visual testing, it's our first line of defense. Once again, this is one of those things I keep beating on. But you have to understand this. If you're going to get into this trade, this is one of the bedrock foundations of it. VT is the most commonly used NDE method. Has been forever. From when we first picked up a stick and sharpened it and went out to challenge the lions and hyenas at the, the watering hole or the whatever they just killed and chased them off, right? We got to make sure our stick is strong, otherwise we might not come back. Good sharp rocks. Hey, the pottery doesn't leak. So a lot of our weld discontinuities, we find them with visual long before we should ever need to use advanced NDT. We find a crack that's open to the surface, or we find porosity that's open to the surface. We don't need another method to tell us that's there. And when we do this, the VT, it's going to help us reduce repair costs because we don't need to chase it with another non-destructive test method. And if the welder and the inspectors are doing this in process, during welding, before welding, after welding, it shouldn't get to NDE a lot of times where we're going to chew up money doing that. So, and most welding codes, they're going to require VT before additional NDE methods come into play.
So we're going to use VT testing of welds prior to welding. So prior to welding, some typical action items that should be included in your routine as a visual inspector or a visual examiner should include. We should look at the drawings and the specifications. What are we doing? What are we making? We should probably have an idea of what's going on there. We should check the qualification of the procedures and the personnel to be utilized. That's kind of outside our scope, as we're talking about VT here, but it does tie in. You want to establish checkpoints. When do I want to look at this? How much of this needs to be welded up before the welder comes and gets me and I take a look at it again? So I probably want to see his fit up. All right, let me see before you start welding. I want to see your first pass. Then I'm going to come back in 3 or 4 passes, depending on how thick it is. And then I'm going to look at the cap pass, the last pass you put on. But the key here is to prepare a plan for how you're going to record your results. How are you going to document this? You might work at a company that's already got this in place, or you might have to be the person that's preparing that plan for recording results. Review the materials to be utilized. Take a look at what's being welded. Is this stuff covered with rust and paint and dirt and all kinds of other deleterious materials and hydrocarbons? Also check the base material. See if it's got a lot of discontinuities. How crappy does this material look like? Once again, rust and gouges and nicks and big scars in it. What do we got going on here? Then you want to check for fit up and alignment of the weld joint. Before the welder strikes an arc on that, if you're doing the inspection, look at that weld joint and make sure that the welder has a reasonable chance at success with that weld joint. And we haven't talked about it here, and this is a little outside, but check the preheat. If it's 30 below outside, you probably want to throw a little heat to your material before the welder strikes an arc on it, so we're not chasing cracks or we don't have problems later on because we didn't preheat that material before we welded on it.
So some common fit-up problems that we could reasonably see during VT. An excessive root opening. The welder tacks this thing up, or the fitter puts it together, and the root opening's a monster. And you're looking at it like there's no way you're going to be able to make that weld. I generally, within boundaries, I give them a little excess on the root openings, let them go a little wide, and I tell them, you're the one that's cutting it out. So That's a you thing. I'll give you a little extra rope, but if you can do it, do it. If not, you're the one that's cutting it out. So that usually kind of brings people back to earth. High-low mismatch. Hey, is the pipe concentric? Have we got our pipe? If you get some thin-walled pipe, it looks circular, but you go to tack that stuff up, the Schedule 10 thin wall stuff, that stuff looks like an Easter egg. You can have a lot of high-low mismatch. Poor bevel preparation. When they cut this, what did the bevel look like? The joint angle? Maybe they didn't cut the joint angle correctly. Weld surfaces. Maybe somebody spilled something on this or whatever. However the contamination is on that weld surface. Maybe it just sat in the pipe or in the laydown yard for 6 months and it's rusty as hell and nobody ran a wire brush across it or a wire wheel or buffed it or whatever. And, you can look at the tacks too. Maybe the tacks are just nasty, full of cracks and porosity, and they're going to consume these things into the weld or whatever. We could have issues there. These are the things that you need to look for.
So when we're welding, there's a lot of items that require control so that the resulting weld's going to come out all right. Visual examination is our primary tripwire, our primary method for making sure that everything comes out right during the fabrication. Visual testing is a very, very valuable process control tool for us. So some of the things that can be checked are the quality of the weld root bead, the first pass we put in there, the root pass. Joint preparation prior to the welding of the second side. So if we've got a weld where we're going to weld it from one side and then back gouge it from the other, well, we probably want to make sure that if we're coming in it from the back side, that we take a look at, the weld prep prior to welding that back side up. Preheat and interpass temperatures are things that we need to take a look at. Did we preheat this thing? Are we keeping it warm enough while we're welding it? And, that's a lot of metallurgy related stuff there. But I'm just throwing that vocabulary out there. Maybe we'll touch base on that in a different, module or a different course. The sequence of the weld passes. We need to keep track of that. Are they stacking these in there right, the weld passes, or do they gobble them all on one side? And, how are they doing this? Are we keeping track of that? Or what about all the different layers? Are they cleaning between each pass? Are they hitting it with a wire brush or a grinder and making sure they're not going to trap any crud in there, any slag or rust or any other deleterious material that could give us problems with the weld quality later on? Are they following the procedure? Voltage, amperage, heat input, these kinds of things. And once again, any of these factors, if we ignore them, could result in flaws, defects, discontinuities, that we could have some quality degradation. We could have issues, problems later on. So these are some things we need to take care of and look at when we're talking about, welds. So a lot of people think that VT commences once the welding has been completed. No. We need to, visual testing of welds starts way before we even strike an arc. And it takes place during welding, before, during, and after welding, where we give it the final blessing, where we look at the surface, the final weld surface. But, this makes sure that we've ensured all the steps have been taken to ensure that we've got a satisfactory weld. So some of the things we need to look at are final weld appearance, final weld size. Did we get enough metal in there or do we get too much? How does that final weld look? Does it look like garbage, or is it a really nice, aesthetically pleasing weld that meets all the criteria, the visual criteria, the specification we're welding to? Is it long enough? What's the dimensional accuracy of our parts that we welded? Did we weld it and just warp everything? Did everything just pull into some kind of twisted Gordian knot, or are we good to go? How much distortion did we have? Do we need post-weld heat treatment? So, the purpose of the final exam is to make sure that the weld is quality, right? Um, Almost all codes and specifications are going to give us, the extent of the discontinuities that are acceptable and, what we can live with on the surface of the completed weld. And this goes back to, like we said, nothing's ever going to be perfect. And each code is going to lay out what you can live with in regards to, defects, discontinuities, flaws, and whatnot. Here's a picture of a completed weld. You can see everything looks pretty good. It's, not all humped up. There's enough weld deposited in there. Pretty solid looking weld. And this is the kind of thing, this is on a piece of pipe, obviously, a round specimen, a round weld, circumferential weld. And this is the kind of thing you could be expected to look at as a weld inspector. So when we're looking at surface cracks, I cut this out of a military document. We're going to fly, hit the flashlight with, 5 to 45 degree angle, and you're moving it towards your face, and you don't want to blind yourself. That's a big one, Keep your eyes above the reflected light beam during the inspection. And then figure out, what kind of cracks can be found by, directing the light at the different angles and, tracing the lengths of the cracks. Figure out what your cracks look like. And you can use a 10 power magnifying glass if you need to, just depending on what. And this is a general overview. Like I said, I cut it out of an old military manual. And if you can't find them or you're not able to do what you need to do with just visual, you might want to use dye penetrant testing, mag particle, or eddy current testing to verify the cracks. So if you have a crack that's a suspected crack, sometimes you need to use other methods that are visual type, but are a little different. We'll get into those. But mag particle and penetrant are just variations of visual testing, and they've got some strengths and weaknesses in regard to finding, surface defects that are open to the surface. So here's some weld examination gauges. We're just going to give a quick overview of these as we go through this. So this is a fillet weld gauge, what they look like. It's a quick way to measure most fillet welds between, 1/8 of an inch and 1 inch. There's some fillet weld gauges that are bigger than that for checking the welds on really monstrous welds, but you can see there it gives you the size. And these work for welding checking both convex and concave fillet welds. Which way the surface is going. So you can see on the left-hand side, we've got a concave fillet weld, and we're using the concave side. And we slide it in there, and if that little part touches, all right, we're good to go. Our fillet weld meets the size requirements of the specification or the drawing that we're working to. On the other side, we've got convex fillet welds. We flip our fillet weld gauge over, and we measure both legs of the fillet weld and see if it meets the requirements. So right there on that blue one, you can see that we're getting we put that little prong down in there, and if it touches the fillet weld there on the left with the little blue arrow, we know that we've reached the requirement for that drawing or specification. And then over here on the second one on the right, where that little blue arrow just appeared, that's telling us that we've measuring a convex fillet weld, and we've achieved the size requirement for that drawing or specification in which we're working to. So weld reinforcement gauges. So we use these on groove welds. There's a couple of different styles, but we use these to measure to see if we've put in enough or too much filler material. We don't like welds really humped up like that yellow weld in the lower left, because that induces stress risers and we can have weld cracking at the toe of the weld. So there's like different types of these, but this is the general theory for using a weld reinforcement gauge. So this is a Palmgren weld gauge. This one we can use in a lot of different ways. This is a proprietary type weld gauge or design. So we can use this to, figure out the size of convex fillet welds, concave fillet welds, the total tolerance for reinforcement, how much reinforcement we've got on a groove weld. So this is one of the gauges that we can use. So you can see there we're using it on the convex fillet weld. There in the lower left, we're using it on the check the convexity of a convex fillet weld. There we're using it, the one that just showed up there, we're checking did we put too much weld in there or not enough? This will tell us. With this gauge, will give us a number. And then over here, we can use it to measure the size of a concave fillet weld. Okay, so here up at the top, you can see I've got circled with that little thin blue line. That would be our pieces of pipe, and that's what we're measuring. Here you can see we've got an 1/8 inch of mismatch. So the high-low gauge is also known as a mismatch gauge. We use it to measure the internal alignment of a pipe. After the gauge has been inserted, we're going to adjust these thumb screws. They're going to tighten down, and then we're going to remove the tool, and then we're going to read what the mismatch is, how much misalignment there is on the inside of that pipe. And then we'll deal with it from there, depending on what our specification is or how our company protocols want us to deal with that misaligned pipe in there. So you can see right there, we pointing to the 1/8 inch mismatch, and that's telling us how much internal misalignment there is with this piece of pipe that we're measuring and getting fit up to be welded. So with most multi-pass welds, they're going to tell us that, especially welds that are critical, they need to be inspected before we get started, before completion, and immediately after completion. And when we're talking about the root pass, which is that first pass that goes into a weld, a groove weld, we're going to want to look at the root surface condition, the amount of penetration if we can, cleaning, surface defects, distortion, all of these things come into play. And you're not going to pick this up overnight, but, be aware, be cognizant that these are some things that you could reasonably, run into or be expected to address if you're doing visual testing. And if the root surfaces of a single welded joint are accessible, if we can access them and take a look at them, we need to look at root penetration, root concavity. What's that look like? Sometimes you got to get a flashlight or a mirror to look inside and see what's going on, if you can get to it. And then drop through and burn through are a couple others. I'm not going to delve into them, but realize there is a whole language involved with that root pass, and the root pass on visual inspection is super critical. And, it takes a little bit of training and knowledge to figure out what you got going on there. VT final inspection, welds that require a final examination of the final surface condition, we're probably going to look at some of these. Size of the legs and throw to fillet welds. How big are the fillet welds? What are we looking at? Contour, reinforcement, and surface finish. What's the weld look like? Is it all humped up and ragged and just a terrible example of what a weld should look like? Or, all right. And usually if there's issues with, if the weld looks absolutely horrible, that doesn't mean that it's always rejectable, but it can mean that you got other issues involved with it. If you've got a lot of issues with, the surface of the weld, or that can also mean you got a lot of other problems with what's going on. Just something to think about. The degree of underfill, undercut, or overlay. And we're not going to dig deep into these right now, but, did we get enough material in there, or did we get too much? Did we run too hot and we got a groove, which is known as undercut, right on the side of our weld? What do we got going on here? How about arc strikes, weld spatter, and impression marks? What do we got going on there? Did the welder strike an arc and then come into the weld groove? Did he strike outside the weld zone and then come into the weld groove? How much spatter is there? What do we got to clean off before we send this thing out the door? These are things that we need to keep track of and look for and address. A lot of finished welds. Here's another finished weld. That's a submerged arc weld. It looks fantastic. We should look for, incomplete fusion, surface porosity. Are there bubbles that are open to the surface? That would be surface porosity. Slag inclusions, cracks. Do we got a lot of distortion? When we welded this thing up, did it just pull and distort on us and just go crazy, or what's it look like? Here's another nice looking weld that was done. We should do it in the as-welded condition, and the as-welded condition is before we send it to post-weld heat treat, before we send it to the heat treat ovens, or before we paint it. Paint doesn't affect the as-welded condition, but you know what I'm saying. So we want to do it in the as-welded condition, immediately after welding, or when it's cool to touch. And there's some weld materials where when we weld them, we've got to let them sit for 28 or 48 hours before we look at them, because there might be delayed cracking type phenomena associated with that material. And the intent of the weld is we don't want to alter it by grinding, chipping, or whatever of the surface. We want to look at it in the as-welded condition. What did that welder do? And then we can see, if there's any other possible defects. The weld must be completed and cleaned of all slag and oxides. So before the inspector's going to look at it, you got to clean all the slag off it and all the crud. It's not the inspector's job to clean the slag and the oxides and all the crud off the weld, the completed weld. Slag removal by any means that may alter the surface of the finished weld should be prohibited. So we don't want to have some kind of method of slag removal. It's just going to destroy the surface of the weld and just mar it and beat the hell out of it. That's not the intent of slag removal.
So what in the heck is the welding world's obsession with gauges? We got all kinds of little tools and accoutrements and little weapons and all these little goodies that we carry with us in these little pouches, right? If you're new to this, why do we do this? Well, what's the point? Well, visual inspection is looking at a defect and saying, yeah, that's nasty. We can't live with that. That is utterly unacceptable. Doesn't meet the criteria. Well, a gauge is going to give us something to measure our acceptance data by. Hey, do we have, way too much reinforcement? Do we have enough reinforcement? We can use it to verify our weld sizes, our reinforcement, our mismatch, what we've got going on there. Otherwise, we wouldn't be able to do that. And then we can objectively document what's going wrong here, right? Or what's going right. Hey, I looked at it with this reinforcement gauge. Hey, this works. And this reduces our subjective interpretation during our inspection phase. If I come along and look at it, me and Joe are using the same tools, the same measurement tools, the same gauges to judge something. So it gives us something objective and not subjective to work off of.
So record keeping, I think I've stressed that a little bit in the previous modules. So with record keeping, with visual testing, we want to document all the discrepancies in a written report, photograph or video recording, just depending on what we got going on. The only way we're going to get the full value of visual is if we keep records. and discrepancies found on the parts that are inspected. Size, shape, location of the parts should be recorded along with other pertinent information such as rework performed or and other dispositions. And we probably want to include some kind of visible record of the discontinuity that makes the record more complete. Maybe it's a sketch or maybe it's an actual picture. With cell phones in this day and age, you got a pretty good reasonable expectation that you could take a picture of it and dump it into a record, to put it in your report. So advantages of visual testing, usually low cost. Tests are simple and pretty easy to apply. There's a lot of other optical instruments available for various types of inspections. Mirrors, lenses, microscopes, telescopes, borescopes, whatever. There's a lot of different types of instruments that we could use. Certain defectors can convert infrared and ultraviolet radiation into visible light or electrical signals that we can interpret. We can use TV cameras, to look at something, remotely. Let's say if it was in a radioactive situation or something, in a nuclear power plant or out at the Hanford nuclear site or somewhere, Oak Ridge, somewhere too hot for people to get in there, but we can send in a robot or a drone and it can look at it, and we use a TV camera to make an evaluation and disposition the parts. If we use more than one wavelength of light, it could give us additional information. VT disadvantages. We're only going to be able to get surface conditions unless we're using a transparent material, and for the most part there are no transparent metals. So this is one of the disadvantages. We can only, check out the surface condition. Or fine detail is important. Large surface areas can become really, really tedious if we really got to go through it with a fine-tooth comb. So that's something we need to realize. Surface conditions do not always reveal internal conditions. Sometimes we've got to come up and we'll do visual, and then we'll hit it with ultrasonic or radiographic testing to check and see if there's internal conditions, discontinuities, flaws, defects that we need to review and address. And resolution is going to be limited by the wavelength of the light we use. And we have to, everything's got to be clean, since the surface coatings can hide defects. Maybe other welding or other non-destructive testing processes, might not need to have the surface nearly as clean. A lot of defects might pass unnoticed, where the object being inspected is large, and we got to work it a portion at a time, or where the defects are really small in comparison to the size of the item being inspected. So, that's something we need to think.
Questions, comments, thoughts, concerns. Gary A. Pace, PE Welding Engineer, Katy, Texas.